So, cool, matrix analysis. So what we're doing today is we'll be concerned with, as the title says, matrices, but from a not as much a linear algebra point of view and more of an analysis, norm, distances, exponential things point of view. And for that, I first want to introduce some basics, which I'm sure most of you are familiar with, just so we settle on the notation, so that we kind of know what we're talking about. So everything that follows will be based on the Schatten norms, or the Schatten P norms, sometimes they're called. So given some matrix, we define its P norm as the sum of its singular values to the p power. We sum them all up, and then we take the p-th root again. P on p is any number not smaller than 1.
Non-integers?
Yeah. And actually, infinity will be included as well, although we have to take a pseudo-prime. Okay. So this is the main object of interest today. There's an equivalent characterization if you don't like singular values as much. You can also, of course, insert the definition of a singular value to instead look at the eigenvalues of a dagger A. So this is still normal A. And we have to take the roots, p over 2. And then 1 over. So if you want to, or if you prefer thinking about eigenvalues, you can also use this as your definition if you want.
Like if singular value is the S in the SVD, like it's the diagonal. But if I just, so it's the singular value of A dagger A. I just mean if A is diagonal and you just take the eigenvalue, then that can be negative. When A dagger A is on the.
Yes, but so are the singular values. Singular values, by definition, are positive numbers.
Okay, but if I have a diagonal matrix, then I can have plus and minus eigenvalues. And if I have the SVD composition of it, it's just the matrix itself.
No, the SVD decomposition. So if you have if A is a diagonal matrix, then the SVD decomposition would, for example, look like this, where V is diagonal. And it flips the signs whenever eigenvalue is negative, it flips.
Okay.
So this is, these are always on negative.
This is a fancy way of saying the singular values are the absolute values of the eigenvalues.
For normal matrices, yes.
No.
Yes. So if A is normal, then this relation does hold. For non-normal matrices, the easiest counterexample is, of course, a simple Jordan block. So this matrix has eigenvalue 0, but one singular value is 1. And this matrix is non-normal. So these can be different. Okay. This is, of course, very general. And in practice, especially in quantum info, one usually works with three values of P, 3 special norms of this type. So the first one is the trace norm. The case P equals 1. So this is nothing but the sum of the singular values. Usually used for states or distances of states. Importantly, if A were a state already, write that. So if A is positive, then the trace norm is the same thing as the trace, because then the singular values are exactly equal to the eigenvalues. In general, there's at least an inequality between these two. The trace is always upper bounded by the trace norm for all A. So that's just as justification why the case P equals 1 is called trace norm, because there's an infinite relation between this value of P and the trace. Okay, then the second one is the Hilbert-Schmidt norm. That's the case P equals 2. The reason this norm is usually considered, among many reasons, I guess, is that it is induced by an inner product. So the Hilbert-Schmidt norm, just the square root of the trace of A dagger A. And of course, this can be written as this is usually defined as the Hilbert-Schmidt inner product of A with itself. So this norm comes from a Hilbert space, or you have very nice Euclidean properties, which is nice for numerics at times, optimization, whatever. And the third one, and after that I also come to the relation between these norms. Third one is what's commonly known as the operator norm, case P equal infinity. So if you take a suitable limit here, then you'll end up with just the largest eigenvalue. So the idea is that as P goes to infinity, the smaller eigenvalues vanish because you're taking the pth root again. So what you end up with, and you can take that as a definition, that the infinity norm is defined as the largest singular value of A. The reason it's usually called operator norm is that you can also get it as the maximal value of A psi. Psi is a pure state. And this is then the usual Euclidean Hilbert space norm. Okay, so yes.
Do I take like any norm actually for the vector? Like, could I take this like, well, it has to be the two norm.
In this?
Yeah.
So if you want to get back the largest singular value, it has to be the twin norm.
Okay.
Of course, in principle, you can take any norm here and call it operator norm with respect to the norm you picked. But in this case, that's a good point. We need this, yes. And these will be the three main norms we'll be concerned with, although sometimes it'll be easier to state things for general P norms. And then these cases will follow kind of as a corollary. Okay, so about some properties of this, like basic properties of these norms. Like every norm, or actually every distance, the P norms satisfy the reverse triangle inequality. Which in my personal experience, but of course you're free to disagree, very underrated inequality. Like at least for me personally, it often came up in places I didn't expect and was very helpful. But as I said, this holds for any metric. There's nothing special about the P norms.
This is equivalent to the triangle.
Yes. Worse. Okay, what is special about the P norms is that they satisfy Euler's inequality. And this will be the basis to relate these norms to each other. So what Euler's inequality says is that if we're given some numbers and they need to have a special relation, they need to be I think, conjugate to each other is the term, which means that 1 over P has to be equal to 1 over Q plus 1 over R. So just if we're given numbers which satisfy this, then the following inequality will hold. Maybe I can then for all matrices, the P norm of the product of two matrices, you can upper bound by the corresponding conjugate Schatten norms. And this is where you need this relation between the numbers. Okay, so this is very powerful because it will imply a lot of other very nice properties about these norms. For example, that maybe. That we have a product of, say, 3 of these norms. Then what we can do, don't think I have a color, but that's fine. So if in these indices, if we choose, say, r equals to infinity and q equals to p, this is satisfied, right? This vanishes and q is p. So for this special case, what Hölder tells us is that we can kind of split off an operator norm, an infinity norm, for free.
It's Q R.
Oh yes, it is. Thank you. And actually, we can do the same by choosing q equal to infinity, and we can split off a from the left. As an example, if B were a difference of states and A and C were unitary, then you can split off these unitaries for free because unitaries have operator norm 1. Actually, unitaries are characterized by the fact that all their singular values are 1. So in particular, the operator norm is 1. Okay, that's one of them. Then the second one. Second one's the following.
And assuming normal, assuming you start with normal arrangements, right? Because you are block plus the identity also gets operating on 1.
No, all the eigenvalues are 1, but the singular value is larger than 1.
Okay, so if you have something with operating on 1, it's unitary.
No, if all the singular values are 1.
Oh yes.
Then it's unitary.
Yeah, okay.
Okay, now the second one. So now we have two Schatten indices where one is bigger than the other. And then we get the following inequality. So the Q norm, the one with the larger index, does never exceed the one with the smaller index. So in a sense, Schatten norms are monotonic. If you just decrease this index, you will always end up with something bigger, or at least not something smaller. And to go to the reverse direction, you will get a dimension factor. So maybe say for all D times D matrices, you can get back to the Q norm, to the larger index, but you have to pay the price of the dimension factor to the power of 1 over P minus 1 over Q. So if we want to learn something about how these norms are related, we just apply this, right? Like we choose p equals 1, q equals 2, p equals 2, q equals infinity, and so on. And I also write that down. Quick. So what this implies is that, well, first of all, the operator norm is the smallest one. Then we get to the 2 norm. Then the 1 norm, that's just monotonicity. And now we want to go back to the 2 norm. So we insert p equals 1, this is 1, q equals 2, this is 1/2. So we get d to the 1/2, or square root of d. And if we do the same with 2 and infinity, we get back, we get another square root of d. So that's how the common p norms are related to each other. And also in general, these bounds are tight. So if we just insert the identity matrix, everything on this side is equal to d. And for pure states, everything on this side is equal to 1. So you cannot, for general matrices A, you cannot tighten these bounds any further. Okay, are there any questions so far? Otherwise, I would come to a first connection to something maybe more familiar to quantum info people, which is the gate fidelity. Okay, so if not,
Is it obvious the inequality bottom left that this is the corollary of the rest of the sum?
sorry, that this is a corollary of
The inequality form, like what you did before.
the Hölder one. So this one is Hölder. From here to here is Hölder.
Yeah.
If you want to see a proof, I can provide one quickly. This one is not Hölder. This comes from the monotonicity of the vector p norms.
Okay, that was fine.
Yeah. Okay, so this is, maybe I shouldn't squeeze this in, but I will. Hölder for p equals the identity. So R will be this index here, and if B is the identity, then all the singular values are 1, and the power comes from the conjugate index. So this is just d to the power of something. Yeah, sorry, I kind of skipped that. If you want to see this argument in more detail, please say so. Otherwise, I would move on to this thing right here. As I said, something that most of you will be familiar with is the gate fidelity. So we are given 2 unitary matrices. And you look at the overlap of the two. We are d times d unitary matrices. So you look at their overlap in terms of the trace, and you divide by d to normalize. You know, the question I want to ask is there some relation between this measure of overlap between unitaries and this norm measure? Because I could, of course, just take my 2 unitaries, take their difference, and look at their norm. Relation to c minus b. Actually, maybe this is not a good measure, because if v is equal to u up to some global phase factor, we'll not detect that. Right? The norm will say, oh, they're not the same, but the corresponding gates are the same. So actually what we should do is also mod out global phase vectors. Just to give this a name, let's call this D infinity, U and V.
Where phi is real, right?
Yes. Maybe for some more motivation, where this measure comes up. Sometimes what you look at is the operator norm of the unitary channels induced by the gates. I'll only briefly mention it, it won't be too important. But the quantity you look at is unitary gate applied to A times the other unitary applied to A. And then because A are usually states, you look at this in the trace norm. So this is usually the channel distance. Actually, you would look at the diamond norm distance, whatever, way too far for this. But there's a simple inequality between this and this thing right here. And I'll only name drop it unless I'm held at gunpoint to prove it. Actually, abbreviate that. So this is a very simple argument based on the triangle inequality, really. That there's this simple relation between this operator norm and just the simple gate fidelity and not gate fidelity gate distance in infinity norm. As I said, I will not use this just for some motivation as to why this could come up. Yes. Yeah. Yes. Because the diamond norm and the 1-1 norm of unitary channels is the same. I don't see any immediate questions. That's either good or very bad. Yeah.
I have a second question.
Yes.
What did you mark there between fidelity and
So what I'm asking about is how, because these are, I would argue, two valid measures of how similar two unitaries are. And given that's the case for both, one would wonder how they related. So how can I bound one by the other and vice versa? Yes. Okay. Okay, the kind of trick to seeing this is the realization, which actually was the definition originally, I think, for the fidelity, but the realization that the fidelity is essentially the two norm distance of the two unitaries. So let's draw that real quick. We take, sorry, we quickly mod out the base vector again. So if we don't take the infinity norm here, which is usually taken for unitaries, but the two norm, we can just write this out. The two norm is just trace of A dagger A, from this case trace of this whole thing dagger times itself. Okay, so we see how we get the overlap via these cross terms here. And these terms, U dagger U, U dagger V, of course, cancel. They're unitary. So we have 2 times the identity from U and BV. And then we get the overlap. V dagger P. For us, we just multiply the thing. Nothing fancy here. Now, of course, you can simplify this further. So trace of identity is just D. And here we can realize that this matrix is just this matrix conjugated. Right, so this conjugated is this, which means that U dagger B dagger. So we have a matrix plus its conjugate, which in total will equal a real number, which is good, as this minimum doesn't make sense.
Then trace lost it.
Yeah, trace would be helpful, that's absolutely true. Trace, and then it's, yes. Okay, so we get the minimum over here, because there's a minus sign here, become a maximum. Now here, because the trace of A dagger is the trace of A conjugated, right? We have a complex number plus its complex conjugate, so that's 2 times its real part. So what this maximization entails is that we are maximizing this real value over the circle, like we're adding a phase. So we'll end up with the absolute value. Which is good because that's what we wanted. We want to see that we take the 2 norm difference, this will be equivalent, these are all equalities, to this thing right here. And we'll have to divide by D in the end. Okay, now the reason this is helpful, of course, is that we already have inequalities between the 2 norm and the operator norm. We can just apply here. So what we'll get is that our fidelity, if we rewrite this, we get 1 minus 1 over 2d, and it's minimum here. Okay, that's just the thing rearrange. And now we use that the 2 norm is lower bounded by the operator norm. And because there's a minus, so we're making what we subtract smaller, the whole thing gets bigger, right? So you can just replace the 2 by infinity at the expense of inequality. For the other inequality, we remember we'll get the factor squared of d. Right, and because this is squared, this will become a factor of d in total, which cancels this d here. So this will be 1 over 2 then. Squared. So that's the relation. Oh, that's one relation. I guess you can find other inequalities getting. So this was just to give you a feeling how one usually works with these operator norms. And there are other proofs for this. You can also use, I'll only tease this, I won't show in detail, but you can also use the C star property of the operator norm. Maybe alternate. you can use that the operator norm squared is always equal to operator norm of A dagger A. Which, if you look at the definition of singular values, that's not super surprising, I guess. And this only holds for the operator norm. That's the only p norm for the which this is true. C star. Property. And this is useful because A dagger A is a positive matrix, so the operator norm will only say something about the eigenvalues then, which makes this whole calculation then easy or feasible. Okay, so this was more from, as I said, more of an example how to use this, or possibly use this for framework.
Star means normal.
Sorry?
Star just means normal matrix. The star property works.
No,
That's the name.
Oh,
Yeah.
I don't know what is C star.
No, so C star that comes from operator theory, C star algebras. So basically, those algebras where the norm has this property. It's kind of a self-referential thing here, but yeah, it's a name. This holds for all matrices A. And actually, even non-square matrices, if you, for whatever reason you have a matrix which is not a square matrix, everything I showed here is still true.
Which D do you use?
Sorry?
Which D do you use in the
Yeah. I guess you would use the smaller one. Like for the relation between P and Q norms? Yeah, the smaller one. Okay, everybody's still on board. Yes.
You use the D, which kind of comes up and which kind of gives you the singular value. Like if you have like a 3 times 2 matrix, you know, like it wouldn't depend on which dimension A dagger A has.
So the singular values of A dagger A and AA dagger are the same. So that's why you can choose which way you order them.
Oh,
I
have okay.
Yeah. So the
and then use a smaller one.
Yeah.
yes, yeah. Of course, the bigger matrix has added zeros in singular values. So the non-zero ones, those are the same.
Okay.
You also have a black hole to
It's true. But the camera is broken. So we are fixed to this view right here.
Yeah.
Okay. Any other questions for now? Else we can move along. So these were a lot of basic things about P norms. And next we can look at some advanced inequalities and properties. So something that's sometimes useful is the duality of Schatten norms. I'll explain what that means, of course. So given any P, one can compute the P norm as a kind of dual optimization problem. You take the trace over X, Y, and now you optimize over all matrices Y, for which the P over P minus 1 norm equals 1. So you get back the P norm if you optimize this trace duality over the unit sphere in this norm here. The reason this index comes up is that this index is conjugate to this one. So 1 over P plus 1 over this whole thing right? We just flip the thing. That's one. So these two indices are conjugate in the usual sense.
So the conjugate of one is the thing.
Sorry?
The conjugate of one is the thing.
The conjugate of one is infinity. And of infinity, it's one. It's a good question because that's my next point. So, for example, the operator norm you get back by optimizing overall. Well, not really states, but let's say states and be imprecise here. One norm, same for one and infinity. Of course, now the question is what's with the other norm? We singled out the 2 norm. So if we plug in 2 here, 2 over 2 minus 1 is 2. So the 2 norm is self-dual. Which also was to be expected because the 2 norm, as I said, comes from an inner product. So it's a norm on a Hilbert space. And for Hilbert spaces, this is always true. The norm on a Hilbert space, you can always get back via this duality. So if this is a norm on a Hilbert space, then you always have this duality formula, where the trace is, of course, the general inner product term. So this is really just a special case of this. We just would have obtained this via Hölder's inequality, which is a lot more powerful than just Hilbert space duality. But this is why.
So for 2 norm,
Yeah.
the y is x.
I mean, you can just take the
X
derivative.
over norm of x, yeah. I guess it would be, yeah. Yes.
Is there anything that breaks if you go to infinite dimensions? You wrote a supremum, and that is only relevant for infinite dimensions.
Right, yeah, for infinite dimensions this also works. It could be that this is not a maximum, I think.
Not all operators have trace class. Trace class.
Right, yeah. Okay, so fair point. This works in infinite dimensions if this is a bounded operator and these are all trace class operators. That's true.
Yeah, I also think the maximum doesn't have to be attained, right? Like in the dimensions.
Yeah, I mean, it needs to be attained in finite dimensions.
Exactly.
That's why I was wondering why you wrote
Yeah.
sub instead of max. But
Yeah, because
that's just mine.
Right. Yeah, so for us we could have written the maximum hurdle. That's true.
In infinite dimension of all norms, only the for bounded operators like the trace norm is not.
For bounded operators, the trace norm need not be finite, yeah.
Which is why this supremum will diverge. Effectively.
The absolute value is not necessary, right? Because you can always split y.
Could be a complex value.
Oh, yes, complex.
Yes.
Without indicating.
That's a fair point if so you can restrict yourself always to the Hermitian subspace and then heretic, but okay. Yeah, then this is real and then it makes sense. Okay. And actually another optimization you can do to get back the 1 norm, you don't even have to optimize overall over the whole operator norm unit sphere. But actually, it's enough to optimize over all unitaries. Over all unitaries, x. This can be simplified even further. One way to see this is by the polar decomposition, for example. So for all A, there exists a unitary. So just that, like if you kind of rotate A, you get back this absolute value of A. Also, this is just name dropping. Don't want to go into too much detail there. Just to say that this is occasionally useful because it establishes a duality between not only between trace norm and operator norm, but actually in some sense between states and unitaries. So really Schrödinger-Heisenberg picture. If you want to be that, if you want to go to that interpretation of it.
Sorry, where do you see the states?
The states are usually connected to the trace norm. So yeah, usually for like one measure for a state distance, just the distance in the trace norm. And actually, if you go to infinite dimensions again, just for motivation, the states live in the space which has this norm. So there's a really intricate relation between this, which in finite dimension isn't as obvious. It's true. Okay. Then another thing. Another thing is that another properties the Schacht norms have is that they are submultiplicative. So we start from some product, the P norm. Then if you remember what we did earlier, by Hölder's inequality, you can split off operator norm. And now the operator norm is the smallest one. So we can upper bound this again by the P norm. And this property that the norm of the product does not exceed the product of the norms it's called submultiplicative. One thing where this is immediately useful is that you can bound exponentials like that. So all norms that are submultiplicative satisfy that you can upper bound this by taking the norm of the exponent here. And you do really need submultiplicativity. So for all P and X. And this will have another nice consequence, which will be related to or which is useful in a scenario where you have, say, a difference of exponential, you want to compare exponentials in terms of the generators. And that's the thing I want to show next.
This is a really weak statement for the trace norm, right?
Oh, you mean the submultiplicative?
No, I mean the submultiplicativity and therefore the.
Yeah. Yeah. And there will be better ways to deal with norms and exponentials later on. That's true. A question so far? Okay, so as I said, sometimes you have a, say, a product of certain matrices, and you want to say you kind of want to quantify the difference of two such products of equal length. And you want to relate these in terms of the difference of single factors. But of course, if you look at this, this is exactly what this property is doing. So the question, can we bound or quantify this by this expression? And indeed you can. This is sometimes known as the telescope identity. And the way it's called that, or the reason it's called that, it's very simple. And this thing is very intuitive if we look at the case m equals 2. So what happens there? So this is not motivation, it's not a proof, of course. But say we have a difference of product of two matrices on each side. Of course, we can just insert a cross term. So you can subtract and then add back cross term x1 by 2. And this helps us because now we can factor out something and get back the expression we desire plus. And once you know this, what I write now will be hopefully obvious, at least not shocking. So here we will force x and 1. So I'm express it like this. On the left-hand side are all the x's of a smaller index. So this is the product of all sorry, I messed this up. It's the product of all the smaller ones. The thing and on the right-hand side are the y matrices with bigger index. K plus 1. And in the end, we want to, or we will take the sum overall. So, okay. Yes. Two indices at the same time, terrible. And hopefully you all agree that this is probably true. And now we just combine this with the non-property up there. So now we look at the norm of this difference. Okay. K minus 1. Normal of everything. Gives first we use the triangle inequality to get the norm down to the summons. Okay, next we can either use some multiplicativity or we can split off infinity norms. Can depend on what you're doing. The better thing, of course, is to split off infinity norms because it's the smaller one. But we'll still use this property. So this p norm, we split off infinity norms of these factors. And as you see, I'm now very sloppy with the indices because usually one introduces like a global maximum of these terms. You'll see in a second. Now, the infinity norm, like every p norm, is self-multiplicative, which means we can pull this norm down to the individual factors. P and then the rest. As I said in the last step, there are two scenarios. Either these infinity norms are already one. For example, if you're looking at unitaries, this vanishes anyway. Or you can, of course, bound these by the maximum of these individual norms. To the m-1, but these are m-1 factors. So as you see, this does scale with m with the number of summons you have, but for certain results, so you can use this to prove the Lee-Trotter formula.
Two times n-.
Sorry?
2 times n, because you have x and 1. Ah, to n-, okay.
Yeah, that's.
The two maximum.
I just took the maximum over all the things in one.
If someone
So, like, of course, I can upper bound this by the maximum of every.
No, that's fine. No, but the term we put at the end is to be the maximum of k, right?
Oh yeah. And you could check the last. In practice, this is often the thing to use. It's just if you want to be more brute force about it, you can also use this perhaps. So one consequence of this, I said you can kind of nicely prove Lee-Trotter formula with this. I will not do that in detail because there are other simpler proofs. But the way you use it there, I think, is interesting. Because there, you look at the special case where both these xj and yj are all the same. So really, you want to estimate mth powers via x and y. And then what happens here, that's why I talk about the maximum as well, is that you get back you can pull down the power. Maximum of x and y. And -1. So just by choosing all these the same, you get this simple relation between mth powers.
Is that tight?
Tight, I don't think so, no. I don't have an example.
No, I think it is.
Yeah,
That's not what I.
it was hard to say, yeah.
No, I think right. So if x is identity and y is really close to the end, yeah, I think it's
Yeah, it sounds like it could be true, yeah. So that's that. Really, this whole thing was a way to show off this nice telescope identity, which also has been kind of like, it's very basic, but it has been what I'm doing rather powerful. So I want to mention it at least. The last thing from this block of advanced properties are just two mentions. I won't go into too much detail there. just so you heard about these things. So there are, of course, even more advanced, even more non-trivial properties for inequalities for p-norms. One of them being the generalized Schwarz inequality. The generalization of Cauchy-Schwarz in a sense. If you want to split off, kind of separate these A and B matrix, then following is true, A and then X, and then X, B, X. And there are tons of others of inequalities of this type. I also have a reference in my notes. I'll also post them afterwards. Just if you want to at some point read up on this, you can have a book linked.
What's the name of the book?
It's just Matthias matrix analysis. Okay, and the other thing is about eigenvalue, singular value inequalities. So of course, for normal matrices, we established that up to absolute value, these are the same. But for non-normal matrices, there are very nice inequalities between these two. There's, for example, Weil's inequality, which states that the product of the kth largest eigenvalues. So I write this down arrow to indicate a decreasing ordering. So the product of the kth largest eigenvalues can never exceed the product of the largest k singular values. And this holds for all k. And actually for k equals d, you have equality as well, always. And one further version of this, you get kind of for free, is that you can take the pth power, and it's still true. And even for all p greater than 0. So there are also tons of inequalities between eigenvalues and singular values. I think the book I linked on this is Marshall-Olkin, which is the standard book on metrization theory.
What does the arrow mean?
Decreased ordering. So lambda 1 down arrow is the largest eigenvalue.
And p larger than 0.
Yes.
You said this derived from the first one?
Sorry.
These two derived from the first one?
No, sorry, these are independent. I wouldn't even know how to prove generalized Schwarz off the top of my head. I only know it's an advanced inequality.
How old is the concept of singular value?
It's a good question. 100 years? 150? I don't know.
Okay.
It sounds like a Wikipedia question, I think. Okay, so next I want to again apply what we did to more fun-related things. One thing being effect of strong perturbations. And I could probably fill 3 lectures about perturbation. This will be very basic, but also kind of nifty thing. I hope you'll agree with this. The question is the following: we have some Hamilton H0, and then we add on to it some perturbation or interaction Hamilton or whatever, depending on some parameter alpha. And think of it as a coupling strength or something. This we call H of alpha. So that's the object. Now what we want to ask about is out of the unperturbed and the perturbed Hamiltonian, respectively, it's a more interesting question. The corresponding unitaries, the corresponding evolutions. Depend on the perturbation. When I say depend, I will again talk about an inequality. But this is the task. We have our dynamics used by this Hamiltonian, and we want to see like how far these unitaries are apart, depending on how strong the coupling is. That's the motivation. The tool for this will be something called 2ML formula. And this is the thing I kind of teased earlier, where this will be a nice formula on the difference of exponentials, matrix exponentials. Before stating it, I will actually prove it, because then it will be way more natural, I think. So we start from 2 matrices x and y, and we introduce an artificial time parameter t. And what we look at now is the product of these exponentials. E to the tx, e to the 1 minus ty. Actually, t could be anything, but we'll only use it in this range. Anyway, this thing you can very easily differentiate. It's just the product rule. So one term will feature an x in the middle, or tx, I guess. And one thing will feature a 1 minus y. No, of course, t stays up there. What am I doing? So it's way better. I was very confused for a second.
Yeah.
And here you can also already see where this is going, because I want to say something about exponentials in terms of difference of generators. Okay, now if we just integrate this back from 0 to 1. Integrate this back from 0 to 1. Then we'll just get this expression, right, at the boundaries. So at t equals 1, this is just e to the x. 1 equals 0, this is e to the y. It's good, that's what we wanted. And on this side, we'll just write out the integral. And in general, not simplify it any further. Which doesn't mean this cannot be very useful. So this is Sturm's formula. The difference of exponentials, you can write as an integral involving the difference of the generators. Okay, now one way to use this, of course, is to use that our norms are submultiplicative. So you have a product, and you want to split up this middle term. We look at some p-norm of these. To the triangle inequality and continuity, we can pull this, pull the p-norm into here. Just in standard norm, integral norm inequality. Okay, now we can split off an infinity norm on both sides. P infinity. Now this vector doesn't depend on t anymore, so we can just pull it out. And we get a, at first glance, kind of bound constant. But we'll see that in our case, this is a very simple expression. Yes. In our case, so we just substitute for x h0, for y h alpha, or actually I times h0 and I times h alpha. Then these are unitary. This expression is 1, and we have an integral over constant function 1. So this whole thing is 1. For x equals I h0. And actually, if we want, we can also plug in a time parameter here. Doesn't really change anything. And again, we take infinity norm, because the smallest one could take any of them. Then this thing is 1, so we get back the difference of t times x0 is t times h. Even h0 minus h alpha is exactly the perturbation term. So this is t alpha interaction term. So in a way, at time 0, we kind of linearized the exponentials, and that's why we get a linear bound here. Of course, as soon as the times get too big, this bound is useless, because this expression right here can never exceed 2. For the simple reason that for 2 unitaries, we just use the triangle inequality. And these are both 1. Much like for states, the difference of unitaries in norm can never exceed 2. But of course, this goes unboundedly. So for small times, this is a good approximation. In particular, it establishes continuity around time 0 in alpha. It's like the smaller alpha, the smaller this deviation will be. But as soon as t gets too large, it's not good anymore, I guess. So that was Duhamel's formula. Yes.
Like in principle, if I want to turn this around, is there a way of from how big the h's vary? I could say something about how much exponentials vary, like other way around.
Not necessarily, because you have something like periodicity, right? Like 2 pi periodicity. So the Hamiltonian, like if h0 is 0 and h alpha is 2 pi identity, then the exponential will be the same. Any more questions?
minutes left. I'm not sure how much you've got left to cover.
Yeah, I was about to say, so I could show one more thing that would kind of stretch our time bound, I guess. I could at least mention it, and if there's interest, I could continue next week, and otherwise, you'll find the details in the notes. That sounds good to everybody. Other questions before we move on to the last thing? Okay, the last thing will be an application that's probably most interesting to people who work with channels, although the techniques we'll use are general matrix analysis techniques that can be useful elsewhere. And what I want to show is that, so we have some linear map, which is positive and trace preserving. If you're not familiar, you can just think this is a map which sends states to states. That's all it does, really. And the following two things are equivalent. By its purity, non-increasing. That is, there's a phi of rho everything squared does not exceed, there's a rho squared for all rho. If and only if the maximally mixed state is a fixed point of phi. So in a way, phi leaves the center of the block ball invariant, if you want to think about it that way. Technical term for this is that phi is universal. So that's a statement that given some channel, the purity can never increase if and only if phi is unital, the maximally mixed state is a fixed point.
Mean purity value increasing? Maybe I'm getting confused.
So if I apply the channel,
The purity is becoming smaller.
cannot increase, I guess. Yeah. Yeah, that's right. Thanks. Okay, so intuitively, especially if you're familiar with channels and PTP methods and so on, you might think this is intuitive, because this basically means that everything gets or should get pulled to the center of the block balls. Purity cannot increase. Either way, it's not immediately obvious how to prove this. And there are multiple proofs for this. A nice one relying on matrix analysis is given via choice inequality. And yes, it's that choice. Choice inequality says that given some positive and unital map and any normal matrix A, this is actually important here, otherwise it need not be true. Phi of A dagger, phi of A upper bounded. Like this. What this means, if you're not familiar, is that this matrix minus this matrix is a positive semi-definite matrix. That's how you induce an ordering on Hermitian matrices. Is A dagger A. Okay, looking at the clock, I don't think I have the time to prove this. I want to give, at least give the main tool, however. And as I said, if you're interested, I can follow up on this next week. So the main tool in proving this is a criterion on positivity of block matrices. So a matrix of matrices. More precisely, if we have some square matrices AXB, A is positive, and B is strictly positive. So all eigenvalues of B are strictly larger than 0. Yes.
Okay, so A can be not Hermitian. What does positive mean in your context for non-Hermitian matrices? Or positive?
Oh, I see.
Sorry, say that again. I'm not.
Like positive normally means that all the eigenvalues of Hermitian matrices are positive or non-zero.
Yeah.
What does it mean for a non-zero matrix? Like this channel does not map Hermitian to Hermitian, but it maps any normal to any other normal.
No, sorry. So phi is a positive map. So it maps positive operators to positive operators. The assumption on this to be true, which should be more clear, is that A is normal. So if A is not normal, this inequality need not be true. Of course, you can still formulate it, because this is a positive matrix, and something dagger times itself is also positive.
Positive, like only Hermitian matrices can be positive, or can there also be non-Hermitian positive matrices?
Only Hermitian matrices can be positive, yes.
So I can do whatever it wants on the anti-Hermitian subspace.
No, because Hermitian times I is an anti-Hermitian times I is.
Yeah, so if you have a map which is specified on all positive operators, then it's specified on the whole space. Because you can decompose every matrix into a linear combination of 4 positive matrices. Okay, so the main tool is this, and the way to prove this, I think that's the most interesting part about this tutorial result here. And it's that statement is that this positive. And the way to see this is to use a similarity transformation. So we apply this matrix from the left. Or it's not a statement, what am I doing? Statement is this is equivalent this. Then, so for all A and B, this big matrix is positive if and only if there's this ordering between the A, X, and B terms. In a way, you can think about it kind of as a determinant. Like if these were numbers and this is already positive, we could just check that the determinant, so A times B, and this X dagger, is positive. And if this is a number, we could just pull it over. So in a way, this is a generalization of determinants for block matrices. We do all the proof. To apply this, hit the dagger. So this transformation, whatever we start with, if this is positive, and we multiply with something from the left, and it's dagger from the right, it's still positive. I hope you'll believe me, otherwise that's that next week. And if you multiply this out, you get exactly this term. On this upper block here. So this is really now a diagonal block matrix. So positivity boils down to positivity of the blocks. That's how it could be. And with this, I would need like 5 more minutes to prove this, so I'll leave it out for now, but this is the main idea. You prove this by going to bigger matrices for which you can in an easier way characterize positivity. Okay. The last thing I'll do is actually prove this purity thing. For that, I'll use a very basic fact about the purity. Which is that for all states, the purity is always between 1 over d and 1, right? For all states. So I set these bounds. And this is satisfied for pure states. And this, in this you have equality if and only if rho is the maximum mixed state. So the maximum mixed state is the unique state which has minimal purity. Purity result, I don't know. So we'll take this as a fact, we'll not prove this. We'll prove this the upper thing. There are 2 directions, of course. So if we start with a unital map, so phi is unital, then you can just plug in the maximally mixed state here, right? So we just choose rho is 1 over d. Then on the right-hand side, we'll have 1 over d. And on the left-hand side, well, we just have that thing, 1 over d, purity of that. Okay, but now because phi sends states to states, this is a state again, so this purity cannot be smaller than 1 over d. So actually, the state has purity 1 over d, which means phi has to be uniform. Again, intuitively, I would say it's clear because what this inequality says is that if we start in the maximum mixed state instead with smallest purity, it cannot become larger. So we're stuck in that point.
Yeah, what's the other way around it?
That sounds reasonable, yeah. Not for the actual thing. Here in choice inequality, we can just plug in a state. So we start from some state rho. Plug it in. So here we get 5 rho squared, because 5 rho is already positive, so the dagger doesn't do anything. So 5 rho squared as an operator for now. It's upper bounded by phi of rho squared in the argument. Okay, so there are differences for the operator. Now we just take the trace. So if 2 operators are ordered like this, then taking the trace does not change this inequality. Let's just straight out. phi squared, nothing happens here. But on this side, we now have the trace of phi of something, and phi was assumed to be trace preserving. So applying phi does not change the trace, meaning this is already the purity. And that's what we wanted to see. This expression does never exceed the purity of the original state. And to be clear, the main tool in proving this was this inequality, which relied on this technique. And you can do a whole other bunch of funny things with this block matrix technique. Okay, so I hope I gave you a brief glimpse into what matrix analysis can be, what certain p-norms are, and yeah, unless there are any questions, then thanks a lot for your attention.